So we've kind of talked about so far what a robot is and how we program them, what they do. So let's kind of talk into what some of the basic systems are and what they do. So we have what's always called the end of arm tooling, the EOAT. This is actually a tool that is attached to the robot arm. Now, let me go ahead and clarify something because the next one is talking about a gripper. A lot of people want to always call the end of arm tool the gripper. However, a gripper is used for gripping, moving, lifting objects. That's not always what a robot does. You also have things like welding, painting, things like that, that are just as common, if not more common, than the basic gripper. So a lot of people try and call the end of arm tool the gripper, but that's not true. The gripper is a type of end of arm tool. It is not the end of arm tool. Does that make sense? So then we have what's called the teach pendant. This is the programming device used when a robot is manually moved through its motions. This is what you use to create a program. It's what you use to get the robot to do whatever it is you're trying to ask it to do. You have non-volatile memory, just like in computers. It's what maintains the contents when the power is removed. In other words, on your laptop, your non-volatile memory is the basic operating system, Windows, or iOS for Apple, I believe. Might be wrong on that one. Might be calling it something weird. But anyway, non-volatile memory is the basic programming that when you take the power off a computer, you remove the battery. This is what allows the main part of your computer to still work. Okay. We have speed. This is the maximum rate of motion a robot arm can go through. Okay. Memory capacity. This is the maximum program size that can be stored in a robot controller. So just like with memory sticks, it's how much of a program or how much of a document can be saved as memory capacity. Does it make sense? All right. So a robot, this is a mechanical device that sometimes resembles a human and is capable of performing tasks on command by being programmed. It operates either automatically or by remote control. And then the last one is we've all heard the term robot applied to human. This is somebody that works mechanically without any original thoughts whatsoever, and automatically responds to the commands of others. I think we've all at some point in time been robots, been stuck in the robot mindset ourselves. It's fairly common. The time where you get tired and you're just sitting there going, okay, do whatever you ask me to do, just So you have the International Standards Organization. Their definition of a robot is that it is an automatically controlled, reprogrammable, multi-purpose manipulator that is programmable in 3 or more axes. And we'll get into what an axis is here in just a little bit. If we don't get to it today, we'll probably get to it next Saturday. So an industrial robot is something that is reprogrammable, has a multifunction manipulator designed to move material parts, tools, or specialized devices through programmable motions for the performance of a variety of tasks. So the biggest key words for a lot of robots tend to be the words reprogrammable and something along the lines of multifunctional. Because if you look at this one, multi-purpose, multifunction, same word, just different ways of saying it. Means that you don't just have one job this thing can do, like pick something up and drop it. This thing could go through several different steps. Does that make sense to everybody? Okay. So the field of industrial robotics may be more practically defined as the study, design, and use of robot systems for manufacturing. So there's a lot of definitions for robots because robots are not simple. So typical applications for industrial robots include welding, because they can get into spaces that we can't and do it very easily and not have to worry about fumes and sparks going in the wrong places. They can do painting. One of the coolest things I've ever seen is you can actually find paint on old line systems like from old Ford and GM and things like that. If you go into their old paint areas where they used to paint the cars, you can find these giant chunks of paint from where it had dripped off the cars or it had just dripped, period. And it's in all these different colors and it's dried over time, so now it just looks like a giant rock. A robot does not have as much problem with that as we do. They can be exceedingly precise, far more so than we have any ability to be. Ironing, assembly. Yeah, assembly is one of those things of it can get real boring real fast. A robot doesn't get bored. A robot doesn't care. It just sits there and says, "Oh, you want me to assemble that 200 million times? Let's go." 200 million times later, oh, another 200 million times? Let's go. And it just keeps going and going for the entirety of its existence. Pick and place, picking up heavier stuff, or just, again, having something that can allow it to be extremely precise and send things to the right places. Palletizing, just putting stuff on pallets and being able to have them be shipped. They can do product inspection through visual cameras, as well as testing. And they have a high endurance, they can use a lot of speed, and they're exceedingly precise. Unlike humans who tire out real quick, we get bored and our mind wanders, and next thing you know, we've got a bunch of defects in something, and we're wondering exactly how that happened, and then we realize that we zoned out for about 20 minutes while we were working. I've seen it happen quite a few times. So manufacturers of industrial robots include, the most common ones I've seen are Yaskawa Motorman, ABB, KUKA, and FANUC. Kawasaki's fairly out there. Some of these other ones I'm not as familiar with, but they are there's lists of robot manufacturers. Um, so there literally is, I think there's up to 26 companies that are into robotics. One of the coolest ones you'd see is now owned, I think, by Amazon. It's called Boston Dynamics. They're actually we're an offshoot of MIT. Um, it all depends on what you need, but there are a lot of different types of robots. And there's a lot of different people that make them. From the toy robots to, I mean, the world is limited, unlimited with robots. Like I said, one of the biggest terms here is what we call reprogrammable, and this is a device that is controlled by a stored program, which can be changed. Multifunction means we can do more than one task. Okay. So the field of robotics may be more practically defined as the study and design and use of robot systems for manufacturing. And that's off of actually Wikipedia. But the production hardware programs and personnel organized into an interactive group for the purpose of converting raw materials, parts, and information into products and services in the world marketplace. Like I said, there's a lot of them out there. All right. So here's an actual assembly line. So what they have here is what they call the teaching booth. And that is what allows them to teach the program initially for the robot. And then they start into production. So each one's going to have its own task. It's going to have things like gluing, it's going to have things like painting, everything. Each machine has its own controller, but all of them are connected back to the main controller. Okay. All right. So typical industrial robot systems, everything revolves around the controller because the controller is essentially the robot's brain. So what does your brain do every time it needs to do something? It checks it. Every part of your body checks back with your brain. So data storage devices have to go back and forth into the controller. Teach device talks to the controller. The robot arm and the controller talk. For the robot arm, it talks to the end of arm tooling and the power source as generally put directly to the arm as well as the controller. All of this to say, basically this thing works as a computer and everything has to go back through the hard drive to work, essentially. Okay. So you have everything again kind of goes back to the controller. You have the robot arm, you have the controller, your power source, and then other additional devices. Generally, you will have a teaching device of some sort. End of arm tooling, you may or may not always have one of those. They actually come without the end of arm tools to begin with. Simply because most robotics companies are not in the tooling business, if you want to call it that. Okay. So robot arms are interconnected sets of linkages, joints, and manipulators, but the primary function is to position that end of arm tool. They usually try and emulate the human arm, but what we can do with 3 joints, they have to do with 6. but these guys can be very specific with the motions that are used to put the end of arm tool in the correct placement. It can be moved by hydraulics, pneumatics, electrical actuators, so on and so forth. It has two basic drive mechanisms that move either in a line or in a rotational fashion. Okay. Any questions so far, guys? So material handling, I'm not quite sure what this one's picking up, but as you can see, looks like it should be something that's quite heavy because they created a forklift essentially for this robot to be able to pick up this product. So what that might be picking up might be something heavy enough that a robot can do it and be more maneuverable than something like a forklift. Which I don't know if y'all have ever tried to run a forklift before. They're not exactly the most maneuverable and easy to use device. Anybody ever driven a forklift? I guess I'll take that as a no. Yeah, they're not easy things to use. They can be quite hard to drive. So this is what they're calling a jointed spherical robot arm, but as you can see, everything here on this guy rotates. There's no linear motion to him. But it shows you right here, this is what allows the whole robot to move at the base. You have the shoulder swivel, the elbow extension, and then here at the very, very front, where you're going to be doing all the positioning to get the tool in the correct orientation, are a total of 3 joints, which would essentially be your wrist joints. They allow you to do pitch, roll, and yaw. So different rotational movements of the wrist. So for your arm sweep and your shoulder swivel, those are actually both motions that are found in your shoulder. So your shoulder has the ability to move up and down in a rotational fashion, and it can also move in a total circle. And then you have your elbow, which just moves in a rotational fashion in and out. So that's why they say it resembles the human arm, only this thing has more joints to be able to do what we can do with our hands. Controller, this is a device which monitors and affects the operational conditions of a given robot. It holds the robot's programs. It is usually a special purpose computer meant specifically for that robot. Contains several ports that allows control of the robot arm, interface with teaching devices and other computers, and to perform other communication tasks. So this thing actually can talk to other parts of itself, or it can talk to a lot of other things, thus allowing for the robot to basically to run correctly and do the task as it's being asked to do. As far as input and output, robot sensors are a input to the robot. Basically, they're just sitting there saying, oh, you are here. Oh, you need to go there. You have production area sensors, basically saying, hey, the product's over here, come get it. You have the teaching station, which is always outside of the robot's enclosure, simply because we don't want the robot to turn around and fling something at its own brain. That would be a bad thing to happen. So the teaching station may be attached to the computer or controller itself. And essentially, again, this thing just works like a giant computer. It's able to hold programs, store programs, be able to interface with things like USB. Um, but it's like I said, essentially it's just a giant computer brain for the robot. So for this robot, they've got this guy, or you have these controllers. What's inside these is essentially nothing but a computer. But this is the robot's brain. The robot does not know anything, how to do anything, how to even have a half thought of anything without that controller. Okay? Essentially, it's a giant anchor for a boat if you don't have that controller to use. Does it make sense to everybody? So robot controller block diagram. So with the controller, it has several different parts to help break this down. You have to have some way to keep your system cool because just like a computer, if it overheats, it can start having a total meltdown and start breaking stuff on its own insides. You have a solid state memory with a power system converter. You have servo drive interface, so the controller is quite literally talking to the servo motors the robots use. Robot controller computer that talks to the input output section. And you can see all the different things it talks to. All of this to say again that the robot controller is what talks to everything, and it is essentially the robot's brain. We've already kind of talked about power sources, but electric is the primary power source. Most of the robots I've ever seen run off of electricity. They don't run off of hydraulic pneumatic. Hydraulic pneumatic is used mainly in the end of arm tool. So it allows the end of arm tool to be stronger and able to do more. So the end of arm tooling or end effector. So again, a gripper is not a end of arm tool. I'm sorry, an end of arm tool is not a gripper. A gripper is a type of end of arm tool. So you might want to make sure you understand the difference, guys. But things we can use for tooling: welding devices, spray guns, allows to be able to spray adhesive or paint or what you need to lubricant of some kind. You have grinding and deburring devices. You have grippers. You have vacuum cups. Basically, anything you need it to do, you can find a way to make it do. A gripper is a device that is mechanically opened and closed. So this is a gripper, guys. A gripper is a type of end of arm tool. It is not the end of arm tool. A lot of things that the robots are used for, things like welding or just material handling. So these are a couple of typical robot grippers. All they do is open and close to pick something up. But as you can see here, you've got a variety of different things that a robot can do. From welding, you can call this almost a type of gripper, but what it is that these slide open, they can slide around a product and pick it up. You have suction cups, you have a deburring tool, drill press, paint sprayer. This one picks up an engine block, and this one picks up was either a side of beef or a side of pork. So lifting an engine, that's not something humans can do easily. In matter of fact, a lot of engine blocks get scratched because somebody's trying to move it manually instead of letting a robot do it. That's what causes seals to not hold and things like that. They found ways to get a robot to do it without causing damage to the engine block. Okay. So we have teaching devices. These are used to program the robot motions. The computer or controller permits the program development and editing while displaying the system operation of the screen. And then you have what's called a teach pendant. This is where you have the programming abilities of the computer, but you can move the robot arm through the desired path to the desired position using the programming process and strictly using that controller. That makes sense. So here's a teach pendant from one of our robots. It's the ABB. Cool thing about this is that you have a joystick to move the robot. The not so cool thing is that it can only move 3 of the 6 axes at a time. You have to switch it over before you can move. So you can move the 2 shoulder joints and the elbow joint, but you can't move the wrist until you switch it over and tell it you want to move the wrist only. Then you have the FedEx teach pendant. So these blue squares over here, each one of these moves a specific joint. One moves it forward, one moves it back. Okay. Then we have what's called the KUKA teach pendant. What you should notice on all of these is the big red and yellow buttons. Those are your E-stops. You press those to make sure the robot stops and can't be moved by other means. Then you have your Moto Man. Again, you have your keys that help you move it through its paces. We have a Mitsubishi robot on one of our assembly lines. So data storage, just like what you use with a computer. These are external permanent storages. I don't think I've seen a cassette tape in years. I don't think they even make them. Floppy disks are still around, as well as hard disks. CD-ROMs and DVDs are around. The only bad thing about those is that once you make them, you can't really change them. Flash drives are extremely common, as well as SD memory. It always depends on where you're at and who's got what they need to create the memory that they need to make. So this is a compact flash card. Degrees of freedom. So let me go ahead and clarify this. This means this is just talking about the joints of the robot. So each joint or axis motion in a mechanical arm is a degree of freedom. It moves the robot to the proper location for the positional axes. These are the main ones. These are the ones, if you're to compare it to your own arm, there are 3 joints that allow you to position your arm in a way to where you can do the work you need to do. After which you mainly use your hands. So if you're going to put your hand over to your keyboard to type, you have to actually use your shoulder muscles as well as your elbow to move your hand over to the keyboard and put it in a position to where you can type in an easy and concise way. That's why these 3 on the robot are called the positional axes. Okay. And if the robot is mounted to a track, that is another positional axis, but those tend to move in a linear fashion. Otherwise, all of these are rotational. Secondly, you have the orientation axis. So once I get my hand to my computer keyboard, I then have to use movements in my wrist to get my hands in the correct position to type. Same thing with this guy. In order to do his job, he has to have the orientation axis to put him in the right place and the right orientation to do the job he's needing to do. Does it make sense to everybody? Do y'all have any questions? So the orientations are all in the wrist. The positionals are all in the shoulder and elbow. You have what are called pitch, roll, and yaw. So a 3D plane to move things through was originally created by aeronautics. So roll, if you have ever been to an air show, you've seen a plane do a roll, where basically the pilot takes the plane and can roll it to either side to make help it make a movement. The pitch of it is to move the nose of the plane up and down, and then the yaw is to move the plane's is the ability to move the plane either left or right. Now, how does this correlate to what we do? Well, with robots, you have to use a similar way of determining where to position the robot. So you have pitch, which is moving the robot on the y-axis. Yaw moves the robot on the z-axis, and roll is on the x-axis. Which once we get into the lab, I can show you all a little bit better. So the work envelope, again, another word for it is the workspace. Okay, so technically your desk or wherever you're sitting to listen to this lecture, that is your workspace or your work envelope. But this is a set of points that represents the minimum and maximum reach and everything in between of the robot's end of arm tool in all directions. So in other words, if you are sitting at a table, everything that you are able to get to from that one position is your work envelope. Okay. So the parts and equipment that you use with this robot must be within that workspace. Otherwise, the robot can't get to it. We bolt these things to the ground through concrete using concrete anchors. It cannot get up and move. So what you have to do is make sure that everything the robot needs is within reach. Does that make sense to everybody? All right, so again, the work envelope, just like if you had to get stuck in front of a desk, it's everything that you have the ability to reach. Only difference is we as humans have the ability to move behind ourselves or wherever we need to move so that we can reach whatever it is we're needing to reach. A robot's reach is a little more limited than ours. Tool center point. This is the point of action for the tooling attachment. It starts off at the faceplate of the robot. So where the robot tool attaches is where that actually starts out before you program it. But it is the point of action for the tooling attachment and must be positioned exactly in order for the tooling to perform the job successfully. In other words, if you have a welder, you need to reposition that tip to the tip of the welder so you don't end up colliding that tip of the welder with anything that's vitally important that could end up destroying your machine. All right, so if you look right here, this is where your tool center point starts, is where this is connected to the robot. So what you have to do as a programmer is take it from there to the tip of the welder or the tip of wherever you need it to be. It can even be in the middle of the space between, but you know, whatever you need to put it. And you can put the tool center point there to allow it not to collide. For something like painting, I don't know how many of you have ever used spray paint. That stuff's not easy to use. You're supposed to keep a certain distance to get good coverage. You have to use certain kind of motions. For a robot, we can tell it the tool center point is at the best point where that paint is going to do its best job. And we can use that to help us position the robot arm even more easily than others. All right, so robot classifications. Okay. Robots are classified according to their work envelope. We have what are called Cartesian or rectilinear. We have cylindrical. We have spherical or polar. And then lastly, we have articulated, revolute, jointed, or anthropomorphic. We'll talk about what those are in a minute. So this guy right here is what you would call a rectilinear because it does exactly what it sounds like. It moves in a rectangle. Okay, the way this guy's going to move is he has the ability to move in a giant square or rectangle because he can move up and down. It can move left and right. Okay, and then this guy is able to move in a 3D plane. So he can also move up and down the 3D plane. Essentially, that's all he can do. He can move in a rectangular space. Any questions on that one? For the next one, you have the cylindrical. Okay. For cylindrical, that means that it moves up and down. It pivots left and right. And as well as being able to move in and out. So basically, it runs completely as a cylinder. The third one down here is what we call polar or spherical, because the way it's going to move is it's going to move in a circle, but it has the ability to rotate over its own head. So the way this guy moves is he can take this and he can sweep it up, he can sweep it down. He can take this in or he can take it back. This guy moves both directions, has the ability to. And then this guy is just able to move however he wants to. He's the, I believe they called it the anthropomorphic, articulated, revolute, jointed, whatever you want to call it. But the way he moves is he's able to take this end of arm tool up and down. He has the ability to move forward and backwards by moving the elbow joint here, or you can sweep it from side to side using the base. So again, this is rectilinear because it moves in a giant rectangle. He moves in a giant rectangle. It's what he does. This one's cylindrical. You can actually see the cylinder here because he's able to move this guy right here. He's able to move it in and out. He's able to move this whole body up and down. And then the base rotates. And then this is, by the way, this body type should look familiar. It's the Unimate, which we talked about in the last class. But again, he works in a spherical or polar run because he is able to use this guy right here to sweep back and forth. It also tilts him up and down. And then this is able to move in a rotational fashion as well. So other classifications, we have things like fixed sequence. We have variable sequence. These are used for pick and place. So in other words, things that are going to pick something up from one place and move it to another. Playback is exactly what it sounds like. It's when you record all your steps and then you tell it to playback. And its ability to do so is what is a classification. There are certain machines that are strictly numerically controlled. They're things like a lathe, which is a machine that's able to spin metal and other items to be able to carve with. Typically, it's done through numerical controls. And then lastly, how intelligent is it? Now, intelligence is kind of a misnomer because robots technically cannot think for themselves. They can make decisions based upon the options given to them by the programmer as to what part of the program they call up, but they are not number 5 from Short Circuit. They are not alive. They do not have reason ability to create and move through different situations. A human has to teach them what situations there could be and how to deal with them. So some other terms, we have accuracy. This is the degree to which the robot can move the tool center point in the work envelope when the remote commands are entered, okay, from the terminal. So this is all about how well it can move that tool center point to a point. Can it do it in high accuracy so that you get it exactly where you want, how you want it, without it having to do a lot of fuss and travel. Repeatability is how accurately the controller can drive the arm back to a point when the program requires. So kind of like how well can you drive back and forth to one place? How accurately can you do that drive? That's your repeatability. Payload. This is the maximum weight which, when you place it a specified distance from the tool plate of the arm, will still permit the robot operation within the specifications of accuracy and or repeatability. Essentially, I don't know how many of you have ever overloaded your vehicle to the point where when you try and put the brakes down, I have seen this happen several times and experienced it, where if you are overloaded in your car and you try and hit those brakes hard, you still end up skidding for another couple of feet before your car is able to make itself stop. That's dealing with payload. The vehicle can only carry so much cargo before it affects how it can drive. And then lastly, speed. This is the maximum rate at which the controller can move that center point to a specified place in the work envelope with the specified payload and without excessive over travel or oscillation. So speed, if you, again, going back to the scenario I just put out, if you have your car overloaded, if you have it at your payload ability or above, and you are trying to deal with getting home with said payload, whenever you are moving it with that speed, you can end up with excessive over travel and oscillation. That's again where If you're trying to stop or you're trying to make turns and such, it's not as easy as if you are under payload. When you're at or over payload in a car, it's a lot more tricky. All of a sudden, it feels like you're driving a boat instead of your car, because the weight that you are carrying in that load is going to make you run all over the road pretty well. So when you're selecting a robot, you need to check for things like, what are you going to need for payload? Are you picking up things that are really, really light, or are you going to be picking up concrete, for example? You need to make sure how many degrees of freedom you actually need. The fewer joints a robot has, the less it's going to cost. Or maybe you need to have a seventh axis where you have the robot mounted to a rail. That is things to think about so that you don't end up with other issues. Drive power. 90% of robots run on electricity because electricity is one of the easiest things to that is available most of the worldwide. If nothing else, you have batteries that can recharge. You have repeatability. How much repeatability do you need? Accuracy. And we just talked about that. The workspace or work envelope dimensions. How big of the space is it? Is it a really big space that you can do all these tasks in, or do you need a smaller robot that has more of a punch to it to allow you to do the same task but with a smaller robot? And again, that's going to save you some money too, because robots, the bigger they are, the more they are. Memory capacity, just like a computer, the more memory you put on that sucker, the more it's going to cost. Programming support, end-of-arm tooling. Again, the end-of-arm tooling is something that you're going to have to either make yourself or have it custom made. Most manufacturers of robots do not, I'll repeat that again, do not make end-of-arm tools. And then you got to deal with environmental requirements. Is this thing going to be in the ocean, or is it going to be part of something else? You know, is it going to be a drone that has to fly through the air? What special considerations do you need for that? That kind of thing. Okay, so we've already talked a little bit about payload. Won't really go over it again. We just talked about it, but it's the maximum lifting capacity of the robot arm under specific sets of conditions. So again, just like your car, your payloads, you know what a payload is by now, guys. It's how much of something can be carried in X amount of time and distance. Degrees of freedom or number of axes. This is the total of main and wrist on the joints on the robot. If the end of arm tool is an integral part of the robot, that can be another axis. It is rarely less than 3 or greater than 6. And the 7th may be like a linear motion to the base for movement. So that's this guy right here. He has 3 here. You have 1 here. You have 1 here. You have 1 here. And then you have number 7, which is this track right here. Okay. Data for axis motion. So this is just kind of a way some people will break it down to you. This guy right here is a 5-axis robot, and it tells you what each one does. So you have the base rotation. You have it able to lift, extend, turn the wrist, and grasp something. It tells you what kind of function they move in. So you have horizontal rotation, vertical linear rotation. You have a horizontal linear rotation, so that's this guy extending. Wrist rotation, and then the gripper that is the tool on this, that is an integral part of this, has the ability to open and close. It tells you how far these things can move and what degree of rotation you can get out of them. So drive source, method used to power all of the axes in the robot. So for this guy is a rack and pinion via air control, so he's a pneumatic robot. He's air actuated all the way. Drive sources will be one or more of things like electric motors. It's extremely common to see most of these guys run by electricity, because most of the time it's right there, the power is right there on hand. Even if you have to use a transformer to step the power up enough that you can get it to run. Most places have hydraulic or pneumatic power sparingly. You have to run it somehow from one end of where your compressor is to where this robot's going to be. Electricity you don't really have to run. You can pretty much find some place there that you can either hook it up to something basic like main power supply, but power supplies are throughout every plant out there. Hydraulics and pneumatics are a little harder to install. Pneumatics really aren't that bad. All you have to do is run hosing from your compressor to your robot and it'll run. Hydraulic, though, you have to not only put a line out to where the robot is, but you have to give it a return line to send the fluid back. It can be really messy. We already talked about repeatability a little bit. This is how many variations will occur. So again, this goes back to how well can you drive the same route every day, all day long, and not miss a turn, not miss your exit, not miss your stops that you need to make. This is typically calculated for the worst case conditions. So with arm fully extended and maximum payload, how well can it get back to that same point? Accuracy is the smallest adjusting movement the tool center point can make to get to reach an exact point in response to the command. So if you were to take a pen in your hand, you were to find a piece of paper and you just bounce that pen up and down on that piece of paper, are you going to get to the same spot every time without a lot of focus to try and get it there to the exact same place every time? Answer is no. Even whenever you stabilize your hand, you're still going to have different movements that are going to cause either the paper or the pen or your hand to move. So you end up with a cluster of dots from your pen instead of one exact point over and over again. Okay, it might be a tight cluster, but it will still be a cluster. It will not be the exact same point every time. But a robot can go back every time. Workspace dimensions. Basically, this is given to you by the manufacturer. They tell you this is where this guy can go. This is how he has to move. This is his space that he needs to work. So here's one that's a drawing. They can give it to you in table form so you don't, basically it's so that you don't put this guy in a space he can't move. Because then he's kind of useless. Okay. All right. So guys, we're going to, all right. So the next thing we kind of look at is speed. So the maximum speed that the tool center point can be moved, it's generally given to you in either English or metric, sometimes usually both. It can be if it's moving in a straight line, it gives you units per second. If it's in a rotational axis, it gives you degrees per second. If the robot has variable speed control, it can give you a range. Um, it can give you the maximum speed possible if there is no variable speed. Memory capacity. So again, just like a computer, the more memory you get, the more expensive it's going to get, but the more memory you get, the better it is to run. So it's always a good trade-off on that. It indicates the length of the program, just like with your computer, just like with a flash drive, just like with anything that stores memory. There's only so much you can store before you have to start deleting things. It can also tell you, you can also limit how many points you can create, which we'll talk about that whenever y'all come in next weekend. And then we also have continuous path motions, and this tends to run as a recording. And the way they rate that is what is the maximum length of time you can record it. So if you remember going back to the old cassette tapes, how long did those record for? Well, it always depended on what you were recording. You know, if you're trying to record something that was over an hour long, you were likely to have to use more than one tape. If you only were listening to something and recording, 10 seconds or so, you had all the recording time you needed. Programming support, this is the measure of availability and quality of the programs for the machine. So each machine, just like a computer, runs certain programs, and how much support you get for that is how much availability do you have for the support for the programs. I don't really always want to say that. So back to the end of arm tools. And I will say this again, this needs to be in your notes. A gripper is a type of end of arm tool. It is not the end of arm tool. And that is generally a very good test question, so you might want to write that down and start memorizing that particular phrase. But most robot manufacturers are not in the tooling business, so this is either fabricated by the end user. So if you're trying to buy this for your company can make the end of arm tool, that's great. Otherwise, they are bought from companies that either specialize in automation or specialize specifically in the end of arm tool. Simply because the robot manufacturers, they focus on the robot itself. The tool, there's so many different ways and shapes, forms, fashions that, again, usually if you're getting a tool, you don't turn to the manufacturer, you turn to somebody that specializes in creating these specific tools. Now, the bad thing about end of arm tools, and I will say this, you don't want to crash one, because end of arm tools can be quite expensive to replace, especially depending upon what kind you're using. If your job has a welding tool and you crash that and you tear that thing up to the point where you got to replace one, that can cost upwards of $1,000 or more, depending upon how complex the design was. That is something that a lot of programmers have to face, is whenever you are using the robot, when you're teaching it, when you're doing anything with this robot, you have to be aware of where that tool is, what orientation it is, and what is around it. I'll give you an example. There's a couple of times I've got a couple of good examples on this. When a robot gets stuck in a certain position, the best thing you can do is back it up from in its program. So what I mean is that if the robot is in a certain position that's like right out here doing whatever it's doing, this is its total path, there might be machinery on either side of this path, and if you tell it to go back to its home position, which might be like right here, you're going to wipe something out, which will tear up your tool, it'll tear up the work cell. It's a bad idea. So what you need to do is go back along the path you came in to get back to where you need to be. That is the only way you should ever go back from that. because if you wipe out the if you start wiping stuff out, your boss is going to come after you. I can tell you that. Um, Another one I can think of is I was working for an automation company, and one day we got a call from a client, and they call us and say, "We need our tool redone." Why? Well, we don't know what happened, but somehow, some way, our tool got damaged. And I think it took us a couple of days to get everything together and get it fixed. So that's downtime for them, which can be extremely expensive for a business. And most of the time, they will not tell you how that happened. They just sit there and go, "Oh, yeah, sorry, we need this. We need you to make this again." Why? 'Cause we broke it. How? Well, we don't know. Somebody touched it. Yep. So that should be something you're majorly aware of anytime you're programming, is where that tool is, where the things around it are, and exactly what you're going to have to do to get from point A to point B without damaging that tool. Environmental requirements. Most robots are designed to operate under typical factory conditions. You have to make provisions to cool the electronics because heat plus electronics are not a good mix. If you have a robot working in some place that's hot, let's say you're in a foundry or a smelting, someplace where they do smelting or make glass and things like that, you're talking thousands of degrees in heat. If you don't make provisions to protect electronics from that, that heat can actually cause the solder in that holds the electronic components to their boards to melt, and you lose connection. That is not a good thing for those of you who don't understand what I'm talking about. That means that essentially your computer board no longer has the ability to maintain hold on the computer chips and the diodes and the resistors and all that kind of stuff. It does not have the ability to hold on to those, thus it cannot make that electrical connection and it fails. That's why most electronics, just like your computer, have that fan that goes across them and pulls out heat, because the longer a computer runs, the more heat it generates. And if it generates too much heat, it can actually damage itself. So whenever you're doing this, you have to take in consideration what your controller's needs are. Does that make sense to everybody? So this is why we actually put the control cabinets outside of where the robot lives, simply so that we can have it not become damaged. And if you happen to have a welding robot, that's going to throw off a lot of heat. So thus we really don't want that heat and the welds and all that hitting the cabinet. Typically it's not a good thing. All right. Y'all got any questions for me?